Hey, we're very happy to have Tobias Hansen from Durham University, who's gonna tell us about AdS string amplitudes from single-valuedness. Yeah, please start.
Okay. Yeah, thanks a lot for inviting me. Very happy to give a talk for you at ICTS today. And yeah, so the motivation for this work is we want to understand how to formulate string theory in curved spacetime, in particular also with Ramond-Ramond flux. Of course, this is a very hard question, so we can start a little bit smaller and try to understand it at least for AdS 5 CFT4, which is one of the most studied example of AdS CFT. But to date, we still don't fully understand the worldsheet theory for this string theory. So the next question is, what would Veneziano do? He would maybe fix the amplitude first. So this is kind of our spirit here. The plan for the talk is as follows. So I will start by talking a little bit about string amplitudes in flat space, a little bit review. Then I will talk about single-valuedness, which will play a big role. Then I come to how we managed to fix the AdS Virasoro-Shapiro amplitude in a small curvature expansion. This is the amplitude for 4 gravitons in type 2b superstring in AdS 5 crosses 5, which is dual to NX4 super Mills. In the next part, I will then talk about the AdS Veneziano amplitude, which is similar, but it's the 4 gluon open string amplitude in an orientifold of type 2b strings in AdS 5 crosses 5. And then in the final part, I will talk about the high energy limit, which is an independent classical scattering computation in AdS. So it's an independent computation of the high energy limit of this string amplitudes. So let's start with flat space. So first we have to talk about what string amplitudes depend on. They depend on many things, like the parameters of the theory. We will take the string coupling to be small, so we will talk only about tree level or genus 0 amplitudes here. Also the string length, square root of alpha prime. And they also, of course, depend on the particles being scattered. So we will consider the 4 graviton amplitude for closed strings or 4 gluon amplitudes for open strings. And they depend on the momenta, which are encoded in terms of Mandelstam's. So here I wrote this twiddle because I use a slightly different definition for closed and open strings, which differs by a factor of 4. And they depend on the polarizations of these gravitons and gluons. So here are the 2 most famous string amplitudes. The 4 graviton amplitudes in the closed string is defined like this. We take out a factor k that depends on the polarizations. And what is left is this famous Virasoro-Shapiro amplitude. For gluons, we also take out a factor depending on the polarizations, and then this trace of this gauge group generators T. And then what's left is this color-ordered amplitude, which is the Veneziano amplitude. Okay, so we have these amplitudes. How can we analyze them and learn more about their properties? One thing is the partial wave expansion. So we can analyze the resonances of poles of these amplitudes and extract or learn what particles are exchanged in this amplitude by expanding the residues in terms of these partial waves, these polynomials depending on the scattering angle. And in terms of for the Virasoro-Shapiro amplitude, the poles in the T channel are all due to this gamma function of minus T. This has poles for all non-negative integer values of T. And if we analyze the residues, we find that we have this infinite number of mass levels. So the poles at T equals 1, 2, 3, and so on. And for higher and higher mass levels, there are higher and higher spins being exchanged. And these string modes, massive string modes, they organize themselves into terms of these linear rising Regge trajectories. Another way we can analyze the amplitudes is by doing a low energy expansion. So this means we expand them in small s and t. And since S and T contain the factor of alpha prime, we can, so the string length, this is an expansion around small strings, short strings. So this makes contact with the low energy effective action, where we have an action for point particles with an infinite number of derivative interactions. And if we do this for the closed string amplitude, we get a supergravity amplitude plus all these derivative contact terms like r to the 4, d to the 4, r to the 4, and so on. And the coefficients here for the closed string case are all odd zeta values. For the open string amplitude, we get super Young-Mills plus, again, derivative contact terms. But in this case, we also get even zeta values like zeta 2, zeta 4, and so on. So this looks, maybe this could be some coincidence, but this fact that closed string amplitudes have only odd zeta values has actually quite a deep mathematical reason. And this has been studied by many people, and this will lead us to the next part, because this has to do with single-valuedness. So let's now talk about single-valuedness and how it appears in string amplitudes. So if we think about these zeta values, they are just defined by, they're just the Riemann zeta function at integer values. And they are related to polylogarithms. If you look at the definition of polylogarithms, you see that zeta values are the same as polylogs evaluated at z equals 1. So let's talk a little bit now about polylogs to understand what it means to have odd zeta values. So first we start with multiple polylogarithms. These are a generalization of the classical polylogs I showed on the previous slide. And they are labeled by a word made up out of letters z1 to zr. And they're defined as these iterated integrals where the letters tell us the poles of the integrand. So they have these properties. Due to that definition, they satisfy this differential relation. So if we take a derivative in z, it means we have, so W stands here for a generic word of letters. So if we take a derivative, we remove the leftmost letter and write a pole term instead. So are multivalued and holomorphic. And for example, if all the letters in the word are 1, we get a power of the usual logarithms. And if we take a bunch of zeros and then a 1, we get the classical polylogarithms, and so on. So there are generalizations of these classical polylogarithms. And obviously, logarithm is multivalued. So
Z, is it right you have on the top that Zi can only be 0 or 1, or can it be more general real number?
For us, there will be 0 and 1 because we will consider the string worldsheet. And we will fix 3 vertex operators for the 4-point amplitude at 0, 1, and infinity. So these are the locations of the other vertex operators. Later on, when we talk about the high energy limit, we can also keep them generic. So yeah, so if you keep them generic, these are called hyperlogarithms, and if you take 0 and 1, they're called multiple polylogarithms.
Okay, thanks.
Okay, so now we talk about a single-valued version of these single-valued multiple polylogarithms. And this single-valued version was introduced by Francis Brown, and they're defined like this. So we again have a generic word W, and they're always given by a sum of products of multiple polylogs evaluated at Z and Z bar, like this. So this is the weight, the transcendental weight is preserved in the sum, and the coefficients C are fixed by demanding that they satisfy the same holomorphic differential relation as the usual multiple polylogs, and that they are single-valued. These two assumptions fix all the coefficients, and you get these non-holomorphic single-valued functions. For example, the example where we take all the poles to be at 1, it's again a power of log, but now log of absolute value. And this next example, 0, 1, is the single-valued version of the D2, the dilogarithm. Okay, now we can come back to multiple zeta values. We define the single-valued multiple zeta values as the single-valued polylogs evaluated at 1. These form a subset of the usual multiple zeta values. And in particular, if you do this for an odd single-valued zeta value, you just get 2 times the usual zeta value. But if you do it for an even single-valued polylog, you get 0. So odd zeta values are single-valued, even ones are not. That means that the closed string amplitudes have only single-valued zeta values in the expansion. Of course, there are also more general nested sum versions of this. So, for example, single-valued zeta of 353 gives a combination of usual multiple zeta values. Okay, so now let's go back to string amplitudes. And now we consider the string worldsheet. So for closed strings, the worldsheet is this Riemann sphere with the insertion of 4 vertex operators, where we can fix 3 of them at 0, 1, and infinity, and we have to integrate the last one over the sphere. So we get this worldsheet integral, and we remember that the low energy expansion has only single-valued zeta values. For the open string, we have the disk with all vertex operators inserted at the boundary, and the one that is not fixed is integrated from 0 to 1, from one of the others, between 2 of the other vertex operators. And these kind of integrals have been studied by many people, and they found that certain 2-dimensional integrals preserve single-valuedness, and the closed string worldsheet integrals are of this type. So that's the reason why closed string amplitudes have only odd zeta values. Okay, but we now want to use this to learn something about curved space. So let's consider now the amplitude in a small curvature expansion. So if we take R to be a curvature scale, later we will take it to be the AdS radius. So if R is large, we have a small curvature, and we consider to the amplitude.
Can I ask a clarificational question?
Yes.
Go back to the slide that had the definition of the single-valued multiple polylog here. So
yeah,
here, so in the box, the L is only labeled by a single integer, right? W is a single integer.
No, this W means word, so it can be a chain of.
So what does it mean that you have to add W1 plus W2 equal to W?
You take all, so the length, so this absolute value means the length of the word.
Yeah.
So you take all words that, so you take all partitions of the length of W and take all the words that have this length.
I see. So W is a word and we just partition it into 2 parts.
No, like if W is length 3, you take all combinations of words W1 and 2 that add up to length 3.
But in the second example, you have L01, right? So what does the 01 mean?
So 01 has length 2.
Yeah.
So you take, for example, if W1 has length 2, you can get the lead 2 of Z. But if W1 and W2 both have length 1, you can get these logs here, log Z times log 1 minus Z bar.
But the point is then the right-hand side does not seem to depend on the actual word, right? It only depends on the length of W. Like if I took L sub 1, 1, wouldn't you be summing over the same set of W1 and W2?
I mean, there are different choices. For example, in this example, there are 2 polylogs where W2 has length 2. This is lead 2 of Z bar. And log 1 minus Z bar times log Z bar. So you just take all possibilities and then.
No, but yeah, I'm just saying, like, if I were to write the same expression for, let's say, L00, would it be the same or different?
it would be different, yeah.
So what term in the right-hand side would be different?
L00 is just log squared of z, absolute value z squared.
Maybe it's not. So in the definition in the blue box, where does that come in? On the right-hand side? So
I mean, it comes in via this differential relation.
Oh.
So in the box, I'm not fixing anything, but then by demanding that it behaves like that, the derivative of it is like this.
Oh, okay, I see. Okay, so it's the differential equation that will fix the relative coefficients differently.
Yes, yes.
I see, for different words.
Together with single-valuedness.
Okay, okay. And then could you show the definition of zeta SV on the next slide?
Yeah. Here, I mean, here,
yeah,
it's a bit sloppy because you have to, the notation of W is different. So,
right.
So you have to convert the notation of zetas to polylogs.
Okay.
So
This
for the W, we would have only zeros and ones, but the zetas, I use a different notation.
But the zetas also depend on a word.
Yeah, you could define them like this, but for example, if I take zeta 2, it means I take this L01. This is the kind of the lead 2, the single valued lead 2. You have to convert the notation a bit.
Okay.
Okay, so okay, we have this. We have this. We want to consider curvature corrections to amplitudes, and to see qualitatively what we could get, what this function A1 could be. We can consider a toy nonlinear sigma model. So this is just a bosonic model, just to see how the worldsheet integral of A1 would look like. So this looks like the Polyakov action with a curved metric. And now we expand this curved metric around flat space. So we have the flat metric, and as long as we at least consider maximally symmetric spaces, the correction looks like x mu x nu over r squared. And we can choose to write it like this. We take this exponential e to the iqx, take two derivatives in q to get down x mu x nu, and then send q to 0. And if we now take all these green things, this integral here with the dx mu, dx nu, together with this exponential, this looks exactly like a graviton vertex operator. So we see that in this small curvature expansion, the metric, the action becomes the flat Polyakov metric action plus a graviton vertex operator with this action, with this operation with q's acting on it. So the conclusion of this is that curvature corrections correspond to insertion of extra soft gravitons. So we could also say the curved metric can be seen as a coherent state of gravitons. So that means at least a part of this A1 should look like a 5-point amplitude. So we have 4 vertex operators from before and this additional graviton, where we take 2 derivatives in q and send q to 0. And this is a flat space amplitude. So that's something we can compute. So let's consider the curvature correction to the closed string amplitude. We have this Riemann sphere with now 5 vertex operators where we integrate over z and u over the sphere. So this just looks like a flat space worldsheet integral with an additional integral over u over the sphere. In the open string case, we now have this 4 open string vertex operators on the boundary of the disk. And since the 5th operator is a graviton, it's a closed string, we have to integrate it over the disk. So we have kind of a open string 4-point worldsheet integral with an additional integral over u over the disk. And these integrals look exactly the same. And these are these type of integrals that preserve single-valuedness. So if we do a small Q expansion, we see that we get single-valued multiple polylogs evaluated at Z. So we conclude that the curvature corrections should qualitatively look like worldsheet integrals over single-valued multiple polylogs. And in the rest of the talk, I will now use AdS CFT to make this precise.
When you say that the integral preserves single-valuedness, it means that the integrand is a single-valued function of U, and the answer is a single-valued function of Z. That means, or?
Yeah, I mean, the integrand is also single-valued in Z, but
Okay.
in general, it's not clear if integrals in general preserve this, right? So,
okay, yeah, just the answer could have been a multiple valued function of Z, right? That's what you mean.
yeah, yes.
Okay.
Okay, so now we can talk about the AdS Virasoro-Shapiro amplitude. And of course, we are here now in AdS 5 CFT4. So in the bulk of AdS, we have type 2B string theory on AdS 5 cross S5. We still have the string coupling and the string length, but now we have an additional parameter, the AdS radius. On the boundary, we have n equals 4 super Young-Mills theory, which is parameterized by the rank of the gauge group and the 't Hooft coupling lambda. And yeah, we have the luxury that in principle, we have three descriptions, like the bulk, the boundary, and the worldsheet. So even though we don't know the worldsheet theory, we will kind of use all of these different descriptions in some way. And we take the string coupling to be small, which corresponds to the planar limit of n equals 4 super Young-Mills. Now, in this holographic correspondence, the graviton amplitude is defined as a CFT correlator in n equals 4 super Young-Mills. And this is a correlator where O is an operator from the stress tensor multiplet. And we will define a certain integral transform that defines for us what we call the AdS amplitude, which is a function of S and T. And it has this small curvature expansion where we will, in the end, completely fix the curvature corrections A1 and A2. And the leading term is just the flat space Virasoro-Shapiro amplitude. Small curvature correction also means it's a correction in strong 't Hooft coupling. Okay, so what is this integral transform? So this is a little bit intricate. From the CFT correlator, we first do a Mellin transform to get the Mellin amplitude M. Then we do a certain Borel transform to get the AdS amplitude A. And then this will be the object that has a worldsheet integral representation. So associated to it is a function GST of Z defined on the worldsheet. If we integrate this over the worldsheet, we also get A. So let's start with the Mellin transform. So this CFT correlator can be defined in terms of the cross ratios U and V. And the Mellin transform is roughly this integral transform, where gamma is a fixed prefactor. And what this does is it relates poles in the Mellin amplitude M to powers of U and V. So if we pick up a pole here in the integral, the location of the pole will appear in the power of U and V. And these Mellin amplitudes have been used already for a long time, and they have many properties of scattering amplitudes. And AdS correlators look much simpler when you express them in Mellin space. Of course, the super powerful thing in a CFT is that we can use the operator product expansion, and it has a finite radius of convergence. And so we can expand these correlators into conformal blocks. This is all very well known. And this relates the correlate or expresses the correlator in terms of the OPE data. So conformal dimensions and spins of the exchange operators and OPE coefficients. And in terms of the Mellin amplitude, the OPE leads to poles in the Mellin amplitudes. so that the location of the poles is related to the dimension and the spin of the exchange operators, and the residues are related to the OPE coefficient squared and some known polynomial of this variable t. So now we can ask, what are the...
Sorry, the fact that this M has only simple poles is a tree level statement probably, right? Loops, it will have cuts or?
No, this is a non-perturbative statement. So this is true for the non-perturbative Mellin amplitude.
Oh, I see.
Yeah. So when we, it has to do with the Borel transform and this sum over M here. So small m is a non-negative integer that so it gives a pole for each descendant of a conformal family. And if you do this sum and do the Borel transform, the AdS amplitude will have cuts. But the Mellin amplitude instead has an infinite number of poles for all the descendants.
Sorry, I missed that. When did you say it will have a cut? If you do what?
If you do the sum over the small m,
I see.
the descendants, and the Borel transform.
Okay. Okay.
And the large. And also, if you do the small curvature expansion. Okay, so the next question is, what are the operators exchanged in this correlator that are relevant for the string amplitude? And the answer is, these are the massive string modes, of course, because they are in the flat space limit, they are still in the curvature expansion. And the masses of the massive string modes in flat space are given by 4 delta divided by alpha prime, where delta is a positive integer. And in a strong coupling or small curvature expansion, we can use this AdS CFT dictionary where we equate the Casimirs, and that gives us the leading dimension at strong coupling. So we just plug in here the flat space masses, and we get the leading dimensions in terms of mass levels. So the AdS amplitude and the curvature corrections will be related like this to the strong coupling expansion of the CFT data. The leading dimensions will be 2 times square root of the mass level delta times lambda to the 1/4. And then we have these corrections that will be fixed if we compute the curvature corrections, and similar for the OPE coefficients. And on the right-hand side, I have a picture of plot from this paper that was computed using the quantum spectral curve. And they compute the dimensions of many of these unprotected single trace operators, for example, Konishi, from weak to strong coupling. So on the left-hand side, we see the dimensions are, the operators just are made out of 3 fields. So the dimensions are 2, 3, 4, 5, and so on. And then when you turn on the coupling, these dimensions intersect, actually, there's level crossing. But at strong coupling, they precisely arrange themselves into these string mass levels labeled by small delta. Okay, so let's go back to the integral transforms. The next one we have to talk about is the Borel transform. And the Borel transform was actually first introduced by João Pineda. Yes?
Naive question about the plot. So you said at R string coupling, these bands are organizing near the different deltas. But what are the individual states within each band? You have like, I don't know, some few number of states in the red band at large coupling.
Yeah. I mean, actually, this plot is not only for R symmetry singlets, so there are many. If we would take only R symmetry singlets, there would be only one here for delta equals 1. So there are a lot of operators. I mean, even for R symmetry singlets, for higher mass levels, there are multiple spins. But these are all that can have different R symmetry content numbers. Like, I mean, they're all kind of single trace operators generalizations of Konishi and so on. Yeah. And it's not clear if you start with an operator at weak coupling, it's easy to write down out of the fields of n equals 4 sub modes. It's not clear at which mass level this will end up if you go to strong coupling. I don't know if this answers your question.
No, thanks.
Okay, so yeah, the Borel transform was introduced by João Penedones as the flat space limit. So he proposed this formula because he noticed that if you do this and take the AdS radius to infinity, this maps every Witten diagram in AdS to the corresponding Feynman diagram in flat space. We also find another interpretation for this, because if you write the low energy expansion of the Mellin amplitude and take these coefficients alpha pq to be the one of the flat space Virasoro-Shapiro amplitude, this sum actually has a zero radius of convergence precisely because of this gamma function here. This grows as p and q grow. And if you have such a sum that is divergent because of a gamma function, what you usually do is a Borel resummation. So you do a Borel transform term by term. This precisely removes the gamma function, and you get this sum here. And we know for the Virasoro-Shapiro amplitude, this for certain values of S and T, this is convergent and gives you the worldsheet integral. So doing the Borel transform makes it possible that there is a convergent sum and that can sum into a worldsheet integral. Okay, so now what do we get for the OPE when we do this Borel transform? Now we do a Borel transform and at the same time the large coupling expansion. And what we get is that the kth curvature correction to the AdS amplitude has poles up to order 3k plus 1. And these numerator functions can be precisely computed by just doing the this Borel transform of the Mellin. So we know how the poles of the Mellin look because it's fixed by the OPE. So we can compute this exactly. The only unknown thing in this equation is the actual OPE data. So now we are ready to make an ansatz for this curvature corrections on the worldsheet. So this is our ansatz. So we propose that we have this sum over 3 channels. This is inspired by string theory computations in superstring and flat space. And then each of these terms should have such a worldsheet integral with some unknown integrand g. And we assume that g has the following properties. It has transcendental weight 3k made up out of these single-valued polylogs and single-valued multiple zeta values. It's a homogeneous degree 2k polynomial in SNT. And to have crossing symmetry, it must be invariant under simultaneous exchange of S and T and Z and 1 minus Z. So how does this look for the first curvature correction? So we
just about the previous slide. So usually the split of the amplitude into 3 terms is done for the open string, right? Now you're doing it for the closed string as well.
It also happens in the closed string. So you get these 3 terms in the intermediate steps, and in the end of the computation, everything you can combine everything together into 1 term. It's because like for the closed string, G closed here is just 1/3, and each of the 3 terms gives the same. But for the curvature corrections, they will not give the same.
So for like k equals 1, this will be some 5-point function.
I mean, we use the 5-point function to motivate that this will be have transcendental degree 3 single-valued polylogs. So we just make it an ansatz, and then we will fix the coefficient. Because we don't know exactly how to compute this from a 5-point function, because we don't know the vertex operators for this string theory.
Or 3 terms is just the ansatz in some sense, like I
Yeah. it's just to have it crossing symmetric, because yeah, if we have here some more complicated integrand, this will not be crossing symmetric anymore. If we have g equals 1, already crossing symmetric by itself.
Right. Okay, thanks.
Okay, so this is then explicitly the ansatz. So it's weight 3, degree 2 polynomial SNT, and we use this combinations of L of Z and L1 minus Z to give it this crossing symmetry. So the L pluses are multiplied by symmetric polynomials, and the L minus are multiplied by antisymmetric polynomials. And then this has 11 rational coefficients. And now matching this with this OPE pole structure, turns out it fixes all the unknowns in both expressions. So the C's in the top expression and the OPE data in the bottom expression. And then this is the solution. So some of the terms actually cancel out. And we can also do the same for the second correction, where we have weight 6.
Sorry, just to go a bit slow. On the previous, I forgot already where these poles in A1 closed came from and how the subleading poles were fixed. Could you say one more time how this was fixed?
Yes. So we had the OPE. So we can do the conformal block expansion of the correlator. If we do this in Mellin space, it means the Mellin amplitude has certain poles and residues.
And those are all single poles.
Yes.
Okay.
But if we now do the Borel transform and the small curvature expansion and the sum over M here, then we get this. So it's an explicit computation, and we can compute. The only unknown thing in the what we started from is the OPE data, so we can compute this. We just basically Borel transform the Mellin amplitude.
Okay.
The OPE in the Mellin amplitude.
So do you have an independent verification that the final answer is correct?
Yes, I will come to that. Yeah, exactly. So one more thing here is how do we know that it's weight 3? One reason we can see it's weight 3 is because we got fourth order poles, and to get fourth order poles, we need a log of z to the log cubed gives fourth order poles. Another way to see the weight 3 is this nonlinear sigma model argument I showed you in the beginning. Because if you do this, you can read off the weight that you need from the 5-point amplitude computation. Okay, so we have a result. So of course we made assumptions, so we need to do checks. But luckily, this result is connected to many other results that have been found in the past. So we have these 4 quantities can be compared with different computations. So we have the Wilson coefficients, which are the coefficients in the low energy expansion. Some of them have been computed from supersymmetric localization. We can compare the conformal dimensions to the integrability results. There was one check of OPE coefficients already done and compared to numerical conformal bootstrap. And then finally, we have the high energy limit, which I will talk about in the last part of the talk, which we can compute a classical computation a la Gross and Mende, but in AdS. So for the first 3 things, I will show you the comparison right now. So first of all, we have the low energy expansion. So it looks like I showed you in the beginning in flat space, but now we also have 1 over lambda corrections. So our result fixes, so we have here now like polynomials in this crossing symmetric polynomials in terms of these crossing symmetric combinations, sigma 2 and sigma 3. And K gives additional powers of 1 over square root of lambda. And we fix 2 infinite towers of Wilson coefficients, all the alpha 1s and all the alpha 2s. And these 4 of them have been previously computed using supersymmetric localization, and they precisely match our result for these coefficients. If we compare results with localization, we can also fully fix the d to the 8 r to the 4 and d to the 10 r to the 4 terms. The next check is the OPE data. So we can extract all this OPE data in these 3 boxes here. And for the leading Redshift trajectory, for instance, where delta is the mass level, so delta equals 1 is the Konishi operator, and we get this result for the dimensions. So we have here the square root of 1 over square root of lambda and 1 over lambda corrections. And this precisely matches with the integrability result. Also, the OPE coefficient of Konishi has been recently computed using numerical conformal bootstrap, and this also matches precisely with our result for this OPE coefficient. And this is not published yet, but was presented this year at Amplitudes. Okay, are there any questions about the Virasoro-Shapiro so far? Then otherwise I can go into the Veneziano amplitude.
One follow-up to the previous question. So in this AK close, when you do the OPE expansion, so most of the data is unknown, right? Like the spectrum and the OPE coefficients. But you're saying the only thing you need to use is the structure of the poles and so on. You don't need the actual.
Yes. So
that is enough.
Yeah, also it's
so
actually like depending on the pole, it depends on the pole how much of this functions, how much unknown data this actually depends on. For example, the highest order pole is always completely fixed by OPE data from the previous order. So only the single pole depends on all the new OPE data.
As an example, at k equals 1, you have 4 of these poles.
Yes.
And
so
yeah.
So we have this 4th order pole. This is completely fixed by the flat space OPE data. And then I think the 3rd order pole, I think, is also fixed. The 2nd order pole depends on the unknown anomalous dimension. And this simple pole is the only one that depends on the new correction to the OPE coefficient.
Okay, so you input the flat space data and
yeah, at each order I input the OPE data from the previous order.
At each order in the curvature expansion.
Yes.
Okay. I see. Thanks.
I use that because I use the OPE data I know, except I mean I use the OPE data I know from the flat space Virasoro-Shapiro amplitude, but not what I know from integrability. So integrability is a check. Okay, any other questions so far? Okay, so let's go to the AdS Veneziano amplitude. So first of all, we have to talk about where we see open strings in AdS 5 CFT4, and type 2b in also in AdS 5 course S5 has only closed strings. But there are so we ask ourselves, what's the simplest AdS 5 CFT4 with weakly coupled open strings? And like as we know from Ashok Sen, of course, and many others, the simplest model is probably an orientifold of type 2b. And this is also like you can see this as n d3 branes near a d4 type F theory singularity, or type 2b with n d3s, 4 d7 branes, and 1 orientifold 7 plane. So in some more detail, this theory would be type 2b gluons on AdS 5 cross S3, where the gauge group in AdS, we call it G, in this case would be SO8 with the same parameters as before. And the boundary theory is now an n equals 2 USP2n gauge theory with flavor group G. And there are also some other possibilities where the group would be instead U4 or SO4 plus SO4. But it seems that we get the same result for these cases because these are just orbifolds of this main example. Okay, so in this case, the CFT correlator is the correlator of an operator from the flavor multiplet.
And
And
the previous slide. So this SO8 symmetry is some geometrically realized thing in the bulk, or what is the, like, is it some R symmetry, or sorry, what is this SO8? So there's some SUN, yeah, there's some USP2N gauge theory.
Yeah, this comes from the D7 brains. Like,
The bulk is just 8-dimensional. You wrote AdS 5 times S3.
yes, that's the fixed point locus of the orientifold action.
Okay. But the two remaining dimensions are just gone, or they, so what? It should be some 10D theory, no? The total thing.
Yeah, I mean that's where the gluons propagate on this.
Oh, I see. The gluons are on an 8-dimensional.
Yeah, on this D7 planes.
I see.
Yeah. Okay, so we have now this flavor multiplet correlator, where I is an adjoint index of this group G. So we have this. We do the same integral transform as before to get an AdS gluon amplitude, and we study this color ordered amplitude, which is the prefactor of this color trace. And again, we do the same small curvature expansion. And in this case, we define the worldsheet integrand like this, as an integrand of this open string integral. So yeah, everything works as before. So we can straight away go to the ansatz we do. And in this case, we don't have maximal supersymmetry. So the ansatz is a bit bigger. We have, in this case, single-valued polylogs.
Tobias, just one clarification. So
yes,
the SO8 gauge field is a gauge group in the bulk. Is that right? That in the bulk you have the SO8 gauge fields living?
Yes. In the boundary is a flavor group.
Yeah. Okay.
Because the boundary has USB2N gauge group.
Okay. On the boundary, yeah. And it's met in the bulk. Okay. Thank you.
Yeah. Yes. So the ansatz now has, again, maximal weight 3K. So we have this sum over transcendental weight from 0 to K, but also lower weight terms. And each term has polynomials in S and T of degree N. And now, in this case, we actually started first out for the first curvature correction G1 to make an ansatz in terms of multiple polylogs. So in this table, we have the number of multiple polylogs of a given weight, and then the number of single-valued multipolylogs at real values. Since the worldsheet integral is only over real values of z, so we integrate z from 0 to 1. We have to consider single-valued polylogs evaluated on the real line. And we can actually first, if we're not sure if we should have a single-valued ansatz, we could just make a more general, not multi-valued ansatz. And even this is enough to fix this. If you compare with the pole structure from the OPE, this already fixes the answer. But it turns out it's automatically single-valued. So we first took this bigger ansatz, which is not single-valued. It's completely fixed, but it's already fixed to be single-valued. And then we see here that at weight 6, it makes quite a big difference to take a single-valued ansatz. We have either 98 or 39 functions. And for the second correction, we directly use a single-valued ansatz. For the second correction, matching with the OPE pole structure fixes everything up to one single coefficient. And so this is the answer. So the ansatz has either 33 or 22 parameters, depending whether we take a multi or single-valued ansatz for the first correction. Looks like this. And the second correction then has already 254 parameters. So we can straight away go to the checks. So again, we fix two additional infinite towers of Wilson coefficients. And for each of these interaction terms, like d squared f to the 4, d4 f to the 4, supersymmetric localization provides one linear constraint. And this was already done for g equals SO8 and for this orbifold case where g equals U4. And in both cases, our result for A100 agrees, which is that it vanishes. However, for the next interaction, we cannot check because we had this one unfixed coefficient. So we can use this to fix the final coefficient in the second curvature correction. And then we can go to the OPE data. In this case, this has not been studied using integrability, only using a classical computation. And in this case, this is our result for the leading Redshift trajectory. And at each order in 1 over lambda, the terms which are highest and lowest order in delta are fixed by the classical solution. And they indeed match the solution. It's called the glued folded open string. And these terms that have here the 1, these would be fixed by a one-loop fluctuation, and this term would be fixed by a two-loop fluctuation. So this, to compare to something, this is still an open problem for semi-classics or for integrability to compute this independently. So here we don't have as many checks as for the Virasoro-Shapiro amplitude. Yeah. Okay, any more questions, or I will go to the high energy limit?
Like there are no questions right now.
Okay. Okay, so then we thought, what's the next step towards the worldsheet theory? Like we would like to do at least some computation on the worldsheet that we can compare to. Gross and Mende showed in flat space that by computing a classical solution to the worldsheet theory, you can reproduce the high energy limit of string amplitudes. And so this is an independent way to compute the high energy limit, agnostic to many details, because you can just compare the exponents, and then it doesn't matter what are the prefactors of the vertex operators, and it's also bosonic only, so it's a bit easier than finding the whole worldsheet theory. So we thought, let's generalize this to AdS. Okay, so first of all, if we already have the worldsheet integral, it's easy to compute the high energy limit. It's just evaluating the integral at the saddle point at z equals s over s plus t. And we get this exponential, at flat space, we get this exponential behavior. And in AdS, the saddle point is at the same location. And we have the worldsheet integral, so we can easily compute the high energy limit. And we would like to compute this exponent for AdS from a string action. So how do we do this? So let's start how this was done in flat space. Gross and Mende did it by minimizing this action here. This is the Polyakov action, where these extra terms here with the delta functions are for the insertion of 4 vertex operators. So if you take e to the minus s, these extra terms just give you e to the I, p, j, x of zj, which is like a dilaton vertex operator. And if you want to minimize this, this is the equation of motion. We also have this Virasoro constraint to ensure diffeomorphism invariance on the worldsheet. And the solution is just this classical solution here. And if we plug this back into the action, this gives us the correct high energy limit, the right exponent that we get in the high energy limit. So to generalize this to AdS, we considered this action. So it's just a very slight generalization. The x's are now in embedding space for AdS. So it's R to the 2 d minus 1. It's d plus 1 dimensional space. And this term with this Lagrange multiplier lambda ensures that we are on AdS. So it ensures that xm equals minus r squared. And we can solve this to eliminate x0 and then expand the remaining d coordinates x mu around flat space. And then if we do this and solve at leading order, we get the same classical solution as in flat space. At the next order in 1 over r squared, we get this equation of motion here. Yeah, the right-hand side depends only on x0, so we can compute it. And here I just wrote the same equation of motion in the notation of single-valued multiple zeta values. So this LZK is just this log of absolute value that you saw before. And now we can integrate this just using this differential relation of the single-valued multiple zeta values. So if we have an integral with a single-valued,
Would you say
multiple,
where this L came on the previous slide? I just missed it. How this L?
So this was the solution of Gross and Mende with the log. So this is a weight 1 single-valued multiple polylog.
I see.
Like this.
Okay.
Okay, and if we have these differential relations for these single-valued multiple polylogs, and if we have an integral with just a pole, it means we have to add the letter at the left of the word. And the anti-holomorphic differential relation is actually a little bit more complicated. So in this case, we add the letter to the right of the word, and then there are some more additional terms. So like this, we can compute the curvature correction to the classical solution, and it looks like this. It's weight 3 single-valued multiple polylogs. And more generally, the leading classical solution is weight 1. The first correction is weight 3, then weight 5, and so on. And now we would like to compare this to the high energy limit of the AdS Virasoro-Shapiro amplitude. So we plug it back into the action. And here I wrote it in a way where F1 is a function of this ratio S over T with function of weight 1. F3 is weight 3, F5 is weight 5, and so on. And if we now take a limit where we take S, T, and R to infinity all at the same rate, we see that F5 and all further terms vanish. So in this limit, this classical solution gives something which is the F1 is the high energy limit of for flat space, and we get this additional weight 3 exponential of something weight 3, which is the correction for AdS. And now we can look at this part with the F3 and compare to AdS Virasoro-Shapiro at the saddle point, and we find it matches precisely. And this, of course, means that at the saddle point, the second correction is just 1/2 the square of the first correction. So we get a result to all orders in S over R, which is that this high energy limit is the flat space high energy limit times this exponential correction. So let me sum up the high energy limit part. So we got we managed to relate the high energy limit of the Virasoro-Shapiro amplitude to a worldsheet action, where we could ignore many details like fermions and prefactors. And the result here is again the result, but note that now I wrote this exponent as epsilon open or closed, because this formula actually also works for the open string case. And we successfully can also compare to the AdS Veneziano amplitude. And the exponent for open and closed string is related like this, as you would expect from a reflection principle. So this is quite a non-trivial relation because these are weight 3 single-valued multiple polylogs. Okay, so I think I'm reached almost the end. So let me sum up what we did. So we managed to fix the AdS Virasoro-Shapiro and AdS Veneziano amplitude in a small curvature expansion by matching the pole structure that is dictated by the operator product expansion with a single-valued ansatz for the worldsheet integral. And we could compare the low-energy expansion to results from supersymmetric localization, the OPE data for massive strings to integrability, and a little bit also to numerical conformal bootstrap. And the high-energy limit matches a classical scattering computation in AdS. Some future directions is, can these dimensions for massive open string operators be independent computed, for example, from integrability or from a semi-classical computation? We are also working on doing this on other backgrounds like tape2a on AdS4 cross CP3, which is the 't Hooft limit of ABGM theory. Of course, we would like to find this go even further beyond the small curvature expansion and maybe get some more results to all orders. And finally, of course, it's important that this can eventually be computed directly from string theory. So there are, of course, the contenders are maybe pure spinors. In this case, vertex operator was already computed, but it still needs to be brought into a covariant form so that we can compute 3- or 4-point amplitudes. And also there's talks that people are trying to compute this from string field theory. Thank you very much.
Thanks, Tobias, for the nice talk.
Yeah, do we have more questions for Tobias?
Yeah, is there any hope of extending this to some M theory calculation, say M theory on AdS 4 times S7?
Yeah, I think we would start with the case where it's string theory. M theory seems hard because it's very useful that we have this flat space result that we can kind of cling on to. Yeah, I guess maybe we can first do this ABGM example and then see if there's some ideas to extend this. I wouldn't see right now how to do it. Do you have any ideas?
So somehow you need the flat space result in order to get the AdS result. I mean, it's essential because a lot of your analysis seems to be independent of the string worldsheet as such, right? I mean, you use some motivation from string worldsheet, but you didn't really, I mean, use a worldsheet calculation directly on AdS.
Yeah. Yeah, but we kind of guess the worldsheet answer. We make an ansatz and then use the OPE to fix it. If we can come up with an ansatz that's general enough and well motivated, then yeah, maybe with this, maybe there's some kind of qualitative computation to motivate a certain ansatz. I guess this would be a 3-dimensional worldsheet then.
Okay, thank you.
Just a comment to that. I think at least in the this AK part in the small curvature expansion, some of the data was fixed using the flat space Virasoro-Shapiro, right? And then we met, like that was right. So you needed the flat space Virasoro-Shapiro amplitude to fix like these higher order poles in A1, for example.
Yeah.
In 11 dimensions, we don't even know the 4 graviton amplitude in 11D, right? Like only the low energy expansion. Yeah.
Yeah, it's both for inspiration and also for yeah, it's a start. If you have the first term in an expansion, it's easier to fix the next one than starting from nothing.
So let's say you wanted to, so in the Virasoro-Shapiro case, you fixed the first two corrections, right? A1 and A2.
Yes.
A3 is just like technically hard, or there is something, is there some fundamental obstruction, or what is the?
Yeah, it's not clear if it's completely fixed if you go on. I mean,
With this method, like you're using.
yes,
really
yes.
from
The first correction was completely fixed with the method. The second term needed a little bit input, and then the basis of these polylogs grows pretty fast, so it could be that it's not completely fixed.
What was the input you needed for the second term for A2?
Like one bit of information.
I see that you took from integrability or localization or something.
Yes, you can. It doesn't matter. You can use one of them. Yes.
I see.
For example, for Veneziano, we used this localization because we don't have integrability.
Mm-hmm. And in the AdS Virasoro-Shapiro, you also use something.
Yes, it's
A2.
for example, you can use the dimension of Konishi, just one operator,
I see.
and then you still has as checks you have localization and all the other operators.
Yeah, makes sense.
Yes. I think the ansatz for A3 for Virasoro-Shapiro has about 1,000 coefficients, and for Veneziano it's 2,500.
For A3, you mean?
Yes.
I see.
So it's 10 times bigger than the previous one. But it's not, it's not clear in beforehand how much gets fixed by this method.
So is there some idea for doing the small going beyond the small curvature expansion, like, because then it seems you'll just these terms just grow very fast, and this method may not be that feasible. Or
I mean, there's the high energy limit is already in some sense to all orders, and there was also recently a paper for the Reggie limit where there's an answer for all orders, but yeah, it's another interesting thing would be like to take this nonlinear sigma model and make it precise, so to really get the result from 5-point amplitudes by modifying a bit the vertex operators, or
you just mean the linear sigma model on the worldsheet, or?
Yes, that I showed in the second part, which we just took a bosonic model just to get the single-valued polylogs. Presumably, there's also like a more correct version of this where you really take the superstring and everything. And then you should, in principle, if you do everything right, you should get this these curvature corrections from this.
Are there any further questions? If not, let's thank him again.
Yeah. Thanks a lot, Tobias. This was very, very useful and helpful. Have a nice talk.
Thank you.
Bye. Have a nice day.
You too. Bye.